Hello, my name is Peter, and I'm going to quickly present to you a video showing the Ansys Fluent simulation for the final project. My simulation here follows along some numbers that we put together in part 1, finding the Mach numbers, the deflection, and the total pressure recovery. I use the Mach number at Mach 0 coming into the inlet, and I also take into account distances that my teammate found for the lengths at point 1 and point 2. The rest of the lengths are found, let's say, artistically and from the distances found in the graphic. So we can get started with the 2D model here. The way I modeled the 2D is such that I can have a pressure inlet along this face, coming along and get to initially experience this initial downturn to cause the first shock towards this angle. And then it gets to experience a second turn right here to cause an additional oblique shock towards this point, with the idea being that the oblique shocks should develop or should slow the flow enough such that a normal shock can appear right along here and then create the Mach flow necessary to flow down this part. A lot of the simulation and sketching is very straightforward. I found distances that are very similar to that of 3 meters, 3.2 for the slightly longer portion off the front. And the rest of the lengths are essentially unnecessary as they are more artistic than they are of use. The position here to be considered as the throat is to be 3.5 meters. Like I said, again, these are very generous numbers and numbers picked just out of general belief and from what the simulation best supplied for our numbers. So if we look at the mechanical portion, we can see how the meshing was done. Meshing was done through very simple, normal means of getting things meshed. I believe if we look at the mesh again, let's get a quick generation here. Meshing is of nothing special. I prefer that when doing simulations, especially with shocks, to have quads instead of triangles. A lot of the people believe that triangles can give you better simulation because of the smaller surface area. And I would normally agree with that. I like to use prime mesh with quad dominance for a lot of these kind of meshes, especially dealing with a lot of oblique shocks, because this gives me the best chance of having a very quick solve and a high chance of convergence. As per usual, surfaces were named and determined for their best possible chances. And with no further ado, let's get into the simulation. So before we spoil anything, we can again see that the pressure inlet is put out the front, while there's a pressure outlet put at the rear. The main thing to keep in mind is that energy has been turned on and viscosity has been set to SST K omega. Very standard settings for something like this. Something else to keep in mind is that specifically for the fluid, we have disabled, let's see if we can get this going here. As per default, this density comes in as a constant, but since we want compressible flow, we're going to set it as an ideal gas. This allows the density to vary throughout the system and thus allow the pressure to vary through the simulation. Another very important thing to keep in mind is that when handling these kinds of simulations, Ansys likes it a lot better when handling, like I said, these compression scenarios to have manual initialization. By manual initialization, you go over to initialization, go from hybrid to standard, go to velocity inlet, set the initialization, which will discard all your previous settings, sets your velocity and sets all your other constants as per necessary, and then lets you run your calculation. So while I wait for this to calculate, usually this takes roughly around between 100 to 200 iterations to really get put together here. We should see convergence and the results that we're looking for. So as per the project requirements, I'm going to be showing you the Mach contours, the velocity contours, the pressure contours, the temperature, and the stagnation for pressure and temperature. And then we can show some of the variations along the plot line. So first, let's get started with the Mach contour. The Mach contour for the system, again, produces that very strong initial oblique shock, allowing the system to come in from an initial flow at Mach 2 and come down to a Mach 1.69. And then we can see again a second oblique shock developing that takes the flow from 1.69 down to 1.25. Unfortunately, we do not seem to have the normal shock developing here, though if we look very carefully, we can actually see a very small normal shock developing here. I believe with some finer meshing, we could definitely get a better normal shock development here. But we could agree that this small region here is the normal shock. And if we look at the speed of this region, we can see that the flow is just below Mach 1, meaning that a normal flow has occurred at this exact point, and in this general area. As you can see, the numbers hover around this magical number, meaning that yes, a normal shock has developed. We can also look through the pressure contour, which shows a very similar picture, showing that as we go through the different shocks, the pressure drastically increases as the flow is being compressed further and further and further. We can look at the pressure contours, as we see a very similar picture, though exaggerated, and showing this normal shock system where it almost blows outwards, where the pressure seems to develop very strongly at this point. This is likely very much so due to the artistic representation of this engine and the overexpansion of this area, causing the flow to detach at this point. We can also see these little waves appearing as the system would not be very stable. We can look at the velocity contour. It shows a very similar system. We can see the velocity again decreases as it passes through the different shocks, both normal and oblique. We can see the total temperature, as the total temperature of the system roughly hovers around the same value, except for areas near the border where temperature seems to rise slightly in areas where the flow is being rapidly accelerated. And then we can look again at the total pressure. The total pressure showing that there is a total pressure drop-off, although very low, you lose very little pressure from the obliques, and a very strong pressure drop-off after this development of a semi-normal shock here. So finally, let's look at the plot line. We can look at some of the XY plots. Again, we can look at the plot for velocity, and we can see that the velocity of the flow decreases as it goes to the system. This line is above where the normal shock occurs, so the values do show that they go back up, but this is mainly due to the throating and expansion of the system. And since the portion of the flow that is represented here is slightly above the normal shock, the velocity can increase above the initial conditions due to this convergent-diverging behavior. Again, we can look at the Mach, and this should reinforce the velocity belief as they are very directly related. We can look at the temperature curve, which should show something somewhat inverted, as the temperature seems to increase through the choke and come right back down as it goes to the exit of the nozzle. We can look at the pressure system, which should show a very similar idea of what's going on. The pressure increases as it steps up and goes through oblique shock 1 and oblique shock 2, and then as it goes through these little waves on the way down. And then we can finally look at the total temperature. The total temperature seems a little less stable as we go along these points, but then again, you can look at the values and see that they're very tightly packed together. So this variance that we see here is unlikely to be representative of much, and more so that this line, if zoomed out, would look very much so, just flat. And then again, we can look at total pressure and see that initial big drop off from that oblique shock, and then a second big drop off from that second oblique. Unfortunately, the normal isn't super well represented here, but you can see that additional drop-off. And then as we pass through the choke, we can go and continue on. So again, this has been the representation for the final project showing the supersonic diffuser system and how it handles the high-speed flow and handling the 2 oblique shocks and normal shock of the system. And by the looks of that, Fluent has decided that this is the end of the video. Thank you so much.